Thank you very much, Jim, and thank you also to the ICSF board for inviting me to this very prestigious series of lectures. My lecture today will be about a central question, not only to the science of climate, but also to climate politics, energy transition, and the social alarm that this climate issue has been causing over the past decades. And so this central question, which is the cause and effect relationship between CO2 and temperature, um, didn't what is kind of recent in terms of science. It didn't start until the 19 mid 1960s. So I'm going to tell a little bit of history before at the beginning, and we will start in the mid 1960s when a group of scientists, including Nobel Prize Shiguro Manabe, started building mathematical models of the climate. And it was clear from the beginning that to cause change in climate, essentially, you need to change the energy content of the climate system. And this could only be done through the top of the atmosphere. So basically, these climate models are vertical energy transfer models. And given the knowledge of climate science, and given the way these models are designed, they could essentially give only one answer, which is that climate change had to depend on CO2 changes. But there was a problem because at that time, in the mid 1960s, the climate was cooling. So the few scientists that were interested in this question thought that maybe they got something wrong or that there was something else that they were not including because CO2 was increasing and the climate was cooling. But one thing that we have to take into account is that scientists like to follow fashion like everybody else. So the fashions in science apparently are called consensuses. So for a scientist to follow the consensus is very beneficial because they get to publish more easily, so their careers are advantageous. And if we had asked a simple question about what made the climate change to climate scientists in the a long time, like for example, without getting into the complications of recent climate change, if we would have asked what caused the Cenozoic ice age in the mid 60s and 70s, most scientists would have said continental drift. Well, from the mid 1980s on, they would have answered that CO2. So clearly, there was a change in the consensus, in the fashion that climate scientists were following. So, if, for example, if we can check this paper from the 1970s that was about Phanerozoic glaciation and the causes of ice ages, and we could see that they were proposing as the cause of ice ages the arrangement of continental masses and their effect on ocean circulation. So what happened then for this complete change of mind, of complete change of consensus into CO2 being the main cause of climate change? Well, two things changed, two very important things. The first one was that around the mid 1980s, it came the realization that the world was warming because of the variability in temperature. It takes about a decade to realize that there's something different going on. And this was very important because now the theory and the evidence aligned, and this allowed to start thinking that maybe the people that made the models were right. Not only that, but they have been able to predict that the world was going to warm before it actually happened. But even more important than this was when in 1985, the Vostok ice core results became available. For the first time, it was possible to measure at the same place both carbon dioxide and temperature for hundreds of thousands of years. And the results were nothing short of amazing. The correspondence was incredibly good. How good is this correlation? When we want to know how good is a correlation, what we do is we make a scatter plot by plotting one variable versus the other. And when we do that for the Antarctic data, we can see that the correlation is very, very good as it gets. In fact, a correlation is deduced because the data falls into a diagonal showing that both variables are changing more or less at the same time. So this data was extremely convinced. And most of the scientists at the time changed their mind and thought, okay, then CO2 is the main driver of climate. And this was about 1985. And the politicians saw the opportunity. 3 years later, the IPCC was born, and all this story started. So we can see why the scientists changed their mind. But, 40 years have passed, and we have new data, and science has advanced, so we can review all these questions. And we're going to do it by going in a travel through time, starting in the deep past, in the Phanerozoic, and checking whether this CO2 temperature relationship and one of them is cause of the other, or they are unrelated. And in the Phanerozoic, I started by looking at the proxy data following this article here, Foster et al. 2017. One of the authors of this paper is Dana Royer, which is the main authority on past CO2 levels. And this is the data that they present about how CO2 levels change over the past 420 million years. But one of the things that we have to take into consideration is that the atmosphere doesn't fossilize. So these proxies are actually quite removed. They are not measuring directly CO2 levels, but very indirectly. For example, stomata is actually a measure of plant respiration. And plant respiration depends not only on CO2, but also on plant physiology. Other proxies are reacting to changes in ocean pH. But ocean pH is also affected by more things than just CO2. So what I did was to download all this data and to check it. And I was very surprised because the data turned out to be quite unreliable. And I'm going to plot it here, one proxy at a time. And this database is made for about 1,200 data points. And this is the main proxy is paleosols, which is plotted here. And then we will have phytoplankton. And we can see that around 30-40 million years, there's quite a lot of disagreement between phytoplankton and paleosols. And then this is boron. And we can see that around 50 million years ago, there is quite a significant disagreement between this proxy and all the others. And then we have stomata, and stomata looks quite different at many places. So another thing that called my attention was that the data appear quite sparse at times, and it was concentrated at certain points. So I ran a 1 million year window through the record and counting the number of records for each 1 million year. And I was very surprised because most of the time there's almost no records. About half of the 420 million years have 0 records or 1 record or at most 2 records. And this is like saying that for the entire Pleistocene, we had only 1 record. We couldn't really say what were the levels of CO2 during the Pleistocene with a single record. So with this data, we cannot really know what were the CO2 levels in the distant past. And then I thought, well, maybe some of these hotspots, at least we can say what were the CO2 levels when they took place. So I checked this 12 million years here between 200 and 212 million years ago and say, well, let's plot this data with more in detail. And it was a complete mess. I mean, the data is all over the place. The uncertainty goes from 300 ppm to over 5,000 ppm. And then we even have some data around here that is at the beginning, which is negative. How can you have negative CO2 data points? It doesn't make any sense. So really, drawing a line through all these points and saying the CO2 levels were like this, it makes absolutely no sense. So if the data is so bad, then that's why there are CO2 models, because it wouldn't make sense to have CO2 models of the past if we had the data, because then we would know, right? So we have models because the data is not there. But when you plot the models, and I'm sure many of you have seen these graphs before, and some will have used them to say CO2 levels were like this or like that in the past. And what we see plotting these 2 models here is that there is quite significant disagreement for the past 350 million years, even though they're based more or less on the same things. So how do we know if we can trust these models or not? Well, I found this paper here, which is precisely a critique of Phanerozoic CO2 models. And I was very surprised because this paper took 3 years to be accepted. And this goes to show why scientists follow the consensus of the time, because if you go against the consensus, you're going to have a very hard time publishing certain things, and your career is going to suffer from that. And another thing that is very remarkable is that this review has 160 pages, so it is actually a book, very detailed study of all the things that go into these models and what is known and what is not known about past CO2 levels and climate. And the conclusions are quite damning for these models. The first conclusion we have already seen is the wide disparities between the curves, as we have seen in the graph, showing that the models are not adequate. But then we have, these models are built on a lot of assumptions about things we know very little about. And there are very general and simplistic generalizations through very long periods of time. So it really, these models are built on our lack of knowledge more than on knowledge. And then CO2 levels are affected by a large number of things, and all these variables, we don't know how they have changed over time. So basically, there is no possibility of combining these complex variables in a meaningful way. So these models are highly uncertain. And finally, and very importantly, they find no relation, no single straightforward relation between levels of CO2 and climate. So basically, we don't have data for past CO2 levels that we can trust, and we can we cannot trust the models either. So what do we have left? Well, at least we have a good idea of tectonic activity. Tectonic activity is the main cause of atmospheric CO2, the main producer of atmospheric CO2. And this in blue here is a tectonic activity model. It has to be taken with a grain of salt, of course, but it's based on the movement of the plates. And we can see that tectonic activity has been decreasing. So CO2 levels were probably several thousand ppm in the distant past. And we can see also that tectonic activity decreases during ice ages. And together with the decrease in temperature, this indicates that during ice ages, CO2 levels are much lower. So what we can say about the Phanerozoic is that we really cannot know what were the CO2 levels then, which doesn't stop some scientists like Dana Roger to say that CO2 is the primary driver of Phanerozoic climate. And surprisingly, nobody calls him on this because obviously nobody has the data to do it. And if you criticize him for saying these things when the data is not there to support it, you can be labeled as a denier and have problems. So basically he goes unchallenged saying this type of things. So let's move forward to the last 50 million years. The last 50 million years, the climate has been very varied, and basically what has happened is that we have entered into an ice age. So 50 million years ago, the climate was much warmer. It was about 14 degrees Celsius warmer than now. And scientists call this a hothouse climate. And then there was a significant cooling during the rest of the Eocene. And scientists call this a warmhouse climate. And then at the start of the Oligocene, the Antarctica froze and we entered an ice age. And this is called a coolhouse climate. And then 4 million years ago, Greenland froze. And then we entered an icehouse climate in which we still continue. So I'm going to follow this article here, Westerholm et al. 2020, because it has the best data, in my opinion, about both temperature and CO2. And they use, for temperature, they use changes in oxygen 18, which is sort of a fatty oxygen because it has 2 extra neutrons. And since it's a little bit fatty, it's also a little bit lazy when it comes to changing phases. So they use the changes in oxygen 18 to infer the temperature of the ocean and the amount of ice. And I'm going to use this data starting at 52 million years ago to avoid all this big volcanic activity from the Deccan Traps and from the North Atlantic igneous province that took place earlier, and the Paleocene-Eocene thermal maximum that messed a little bit the data. So we're going to start in the middle of the early Eocene climate optimum, and we're going to use, instead of oxygen 18, we're going to use the temperature data that the authors of the paper also provide, because I think it will be more convenient for the audience. With regard to CO2 data, in this paper, they use over 3,000 CO2 data points from all this bibliography. It's very complete as far as it goes. They use also the Foster et al. 2017 reference that we have seen previously, but only for the last 66 million years. And when we analyze what happened, we all know that over the last 50 million years, both temperature and CO2 have decreased during the Cenozoic. So when we plot the temperature, what we see is something like this, and we can see very clearly that there was a pronounced cooling during the Eocene until a tipping point was reached when Antarctica froze. And then we had a little bit of warming here, about 2 degrees, during the Oligocene and the early Miocene until the mid-Miocene climate optimum. And afterward, a tipping point took place. And this one is not well characterized, but my opinion is that was probably the uplift of the Himalayan mountain range. And then from the late Miocene to the Pliocene, there was another cooling period until another tipping point was reached when Greenland froze. Okay, so Westerholm et al. Do not plot the CO2 changes together with the temperature changes. And I think that they don't do it because it doesn't look very much like they correlate. So this will be the data that they use plot more or less at the same scale. And we can see that there's only correlation over the last 4 million years or so. So if they don't plot the data, what do they use it for? Well, they present this figure, which is figure 2 in their paper, in which they do a scatter plot similar to the one that I showed at the beginning for the Pleistocene. And they indicate there the present CO2 concentration and the CO2 concentration that they expect in the year 2100 if RCP 8.5 scenario is followed. I'm going to reproduce this figure using the same data, but I'm going to change it so it's a little bit clearer. So I'm going to plot CO2 in the vertical axis and temperature in the horizontal axis. And so high CO2, high temperature data will be in the top left corner, and low CO2 and low temperature data will be in the bottom right corner. And if the data will be color coded as they do to show to what period it corresponds. And if you remember the slide that I put at the beginning, if there is a correlation, the data should be close to a diagonal, showing that when one of the variables changes, the other changes too. So when we do this and we plot the data, what we're going to see is that essentially only one of the variables is changing. So either the temperature or the CO2 changes, but not both at the same time. And once we reach the mid-Miocene and the cooling that takes place there, only when it reaches the Pliocene and Pleistocene does the data follow the diagonal. So essentially, what we see here is there are some times when just the CO2 changes, and the first two I'll be cautious about because the data is not very good. So they could be partly an artifact of the data, but the third one is very clear. And then there are other times when only the temperature is changing, and we will have the first one will be the Eocene cooling, then we will have the freezing of Antarctica, and then the cooling that takes place in the late Miocene, from the late Miocene to the Pleistocene. So as you can imagine, this doesn't show correlation between CO2 levels and temperature, and this is reflected in a low correlation index. So the amazing thing about this is that the authors of the paper shockingly claim the opposite. They say that the present climate is comparable to the Miocene, and this is absolutely absurd because the Miocene was much warmer, and Greenland didn't have any ice sheet in it. It was covered in the forests and full of animals. And they say that if CO2 emissions continue unmitigated, Earth's climate will move abruptly into hothouse climate. I mean, their own data is saying this is not correct. Let me tell you, in my scientific career, it's very extremely rare to see a paper where the authors claim the opposite of what their own data shows, because basically this doesn't, it wouldn't go through the reviewers, wouldn't be approved by the reviewers that you claim the opposite of the data that you show. But climate science is very special kind of science. So we go back to the slide because I would like to study this here. This is what calls my attention the most. This decrease in CO2 that took place during the Oligocene. And Westerholm et al., they do plot the CO2 in the supplemental information, although I had to stretch the vertical axis because it's so compressed and in a logarithmic scale that I think they do it so people won't realize that CO2 and temperature have little to do in the data that they have. But we can see very clearly here that during the Eocene and Oligocene, there is a high CO2 levels, about 700 to 850. And then during the late Oligocene on, there's essentially low CO2 levels, around 300, 400 ppm. So we have from the mid Oligocene to the late Oligocene, a huge drop from one level to another. And this was very interesting to me, so I plotted the data here with more detail for this period. And what we can see here is that from the mid Oligocene to the late Oligocene, there was a slight warming, not much of a warming. But curiously, CO2 levels completely collapsed from about 800 ppm to about 300 ppm or less. So this is about a 60% decrease in CO2 levels. It's more than a halving of CO2 levels, while the world, the planet, was actually warming, not cooling. So the Oligocene is like a, something, it's a period that nobody is discussing this because this data is available. Other people are studying the Oligocene. They don't talk about this. I've been looking for articles, what do scientists say about this? And I couldn't find any. I don't know if there's any of them, but I couldn't find them. It's like, there is a secret pact not to talk about Oligocene CO2 levels and what happened to the CO2 during the Oligocene. And the question is, what was happening during the Oligocene that could have affected in this way CO2 levels? And the thing that was happening, the most important thing that was happening during the Oligocene was the development of the Antarctic circumpolar current. During the Eocene, South America and Australia were very close to Antarctica, separated only by shallow waters. But as they started to separate and the Drake Strait opened and the Tasmanian Gateway opened, the Antarctic circumpolar current started to develop due to the rotation of the Earth and the Coriolis effect, and the winds associated with it and the current isolated Antarctica from the rest of the planet climatically. And this was what caused the freezing of Antarctica in less than 1 million years. And as the current was becoming stronger and stronger, the warm currents from the tropics and the warm winds couldn't reach Antarctica anymore. So there was actually global warming because that heat was being kept by the rest of the planet. And the other thing was developing as a result of the Antarctic circumpolar current was the Antarctic bottom water, which is a very large body of very cold, very dense water that occupies the bottom of the Atlantic, Indian, Pacific, and Southern oceans. And basically, this very cold water was created in this period. And since CO2 dissolves better in cold water, essentially, the creation of the Antarctic bottom water must have sequestered all that CO2, and that CO2 is still there because it cannot go anywhere else. So we will move now to the Pleistocene, and we go back to this graph that in which there is a correlation. But the thing is that in 1890, Thomas Chamberlain made a significant contribution to the scientific method when he developed the multiple working hypothesis method, in which every hypothesis possible should be considered as a way to prevent that the scientists would get too fond of their favorite theory and forget about other possibilities. But sadly, you know, the multiple working hypothesis method has fallen into disuse. And so we will have that most people in the audience will interpret this graph as that changes in temperature are causing changes in carbon dioxide. And most scientists and the rest of the people will say that it is actually changes in CO2 levels that are causing the changes in temperature. But then we have the third possibility in which nobody is thinking, nobody is considering, which is that we have a third factor, another cause, that is causing the changes in temperature and in CO2 at the same time. And the thing is that we do know what this factor could be, because we do know that the shape of this graph is being caused by Milankovitch forcing, by Milankovitch cycles that change the orbital configuration of the Earth. And the thing is, to distinguish these possibilities, we have already done the experiment. This is the figure that I presented earlier, showing the strong correlation between CO2 and temperature in Antarctica. And over the past 200 years, we have increased CO2 levels tremendously. And literally, CO2 levels are going through the roof, at least through the roof of this graph. And the temperature of Antarctica isn't changing. So basically, we have destroyed this correlation. We have shown that this correlation is not due to changes in CO2. And we have shown that changing the temperature of the planet doesn't change the temperature of Antarctica either. So as Richard Feynman would say, it doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with the experiment, it's wrong. So clearly it's wrong. And we have this paper from 2007, which hasn't been paid too much attention, that says that the warming of the southern hemisphere and the deep sea took place before atmospheric CO2 levels rose and tropical warming took place. They say that between 19 and 17,000 years ago, the bottom of the ocean warmed by 2 degrees about 1,000 years earlier than the rise in atmospheric CO2 and of tropical ocean took place. And this is the data that they show. And here at the bottom, you can see, I don't know if you can see my arrow here, my arrowhead, but the Pacific temperatures are shown here with blue dots near the bottom. And we can see that they started warming 19,000 years ago. And by 17,000 years ago, when the tropical Pacific started to warm, they had already warmed by 2 degrees. And let me tell you, warming the bottom of the ocean by 2 degrees is quite complicated. It requires a lot of energy. And we can see also here with the green diamonds that the surface of the South Pacific started to warm also around 19,000 years ago, while the increase in CO2, which is at the top, started about 1,000 years later. So basically, we can say that Milankovitch Milankovitch orbital changes caused the warming of Antarctica at the beginning of the interglacials, and Milankovitch orbital changes caused also the warming of the Southern Ocean and the bottom water that were responsible for the increase in CO2. So that's the reason why they do correlate. And today's global warming and CO2 increase cannot warm Antarctica. So that's why today they no longer correlate. So this is evidence that it is Milankovitch forcing what is causing both the temperature changes and the CO2 changes. And they are not being caused one of them is not causing the other. It is Milankovitch. And this is known by some scientists which write about the role of the Southern Ocean in the variations of CO2. So basically, in science, things are usually known. You just have to look for the papers. So let's move to the Holocene. And you probably know this graph that I made from Marcotte et al. 2013 data. I just processed the data slightly differently to not destroy the variability, to preserve the variability of the data. And it shows that there was a Holocene climatic optimum followed by a cooling neoglaciation, as it was known before. And the shape of this curve has become under a lot of fire, a lot of controversy, because as we will see, CO2 levels don't agree much with this. And the shape of this curve has been caused by Milankovitch forcing, again, Milankovitch cycles, because obliquity peaked around 10,000 years ago, and northern summer insolation peaked around 9,000 years ago, and they have been both declining since. And how do we know that the shape of this reconstruction is more or less correct? Then we can use the information from glacial advances present in the Solomina et al. 2015 paper, in which they take all the glaciers of the world and group them in 17 regions, and then they count the number of regions that were experimenting glacial advances at every century of the Holocene. So since glaciers advance when it is cold, what we can do is we can invert this graph, and we can see that basically it has a very compatible profile. So there is quite a lot of agreement between glacier data and temperature proxy data, and we can even recognize here several of the most better known events of the Holocene. Okay, so if we look at CO2, the problem is that once again, there is absolutely no correlation between temperature data and CO2 data, because CO2 was decreasing during the Holocene climatic optimum, most of it, and then it was increasing afterwards during the neoglaciation. And this is a real problem because, models produce this curve, this result, and clearly they are not responding sufficiently to Milankovitch forcing, and they are responding too much to CO2 when they shouldn't. So that's the controversy that there is right now, and I think they want to change the data for the Holocene to match the models, because it is easier to change the data just by picking different proxies than to change the models, which is really complicated. So one interesting thing is that CO2 changes follow much better the temperature of Antarctica from an ice core. So this again shows that CO2 levels are following the temperature of the high latitudes of the southern hemisphere, which due to Milankovitch forcing, it's opposite. Summer insolation in the southern hemisphere is opposite. So that's the reason why these curves have this shape. So if we now move to the Little Ice Age, I would like to show this reconstruction of the Northern Hemisphere temperature from Moberg et al. 2005 that spans from the year 1000 to the year 1590. So these 6 centuries, it took place a very great cooling, one of the biggest of the Holocene, from the medieval warm period to the Little Ice Age. So when we check what was doing CO2 during that time, what we see is was doing nothing. I mean, there was absolutely no change in CO2 while the Northern Hemisphere was undergoing a significant cooling. And probably the Southern Hemisphere was also quite affected, perhaps not as much, but quite affected, and yet no change. Once again, no correlation between temperature and CO2. So we can move to the conclusions and say that there is no correlation between temperature and CO2 except during the Pleistocene. And then the correlation during the Pleistocene is likely due to Milankovitch forcing acting on temperature and CO2. Therefore, paleodata support that temperature and CO2 are not a first-order cause of each other. CO2 cannot be a primary driver of climate. That doesn't rule out that there is a second-order effect. I mean, some effect could take place, but clearly they are not a first-order cause of each other. And then data from the Oligocene, Pleistocene, and Holocene suggest that changes in the temperature of the Southern Ocean are the primary drivers of changes in CO2. And finally, what we all know, that there is no climate emergency and no need to reduce human CO2 emissions, and that climate science is trapped in a false paradigm that will take decades to correct. And this is the bibliography that I have used to make this talk. And then I would like to do a little bit of promotion of the 2 books that I have published on my YouTube channel and my X account. And with this, I conclude my presentation.